Hello and welcome to the direction video for Lab 4. In Lab 3, we're going to talk about the basic coordinates and seasons. All right, so what you have so far seen uploaded to the Canvas page under the Lab 3 module is this document. It's called the Basic Coordinates and Seasons Student Guide. Okay, so when we do labs from this particular website, which is a simulation education website, all the labs are going to have this similar look, and they will all be called student guides. They allow for places to answer the questions within the document themselves, which you can either type in using a PDF modifier, a program, such as Preview on a Mac, or some sort of Adobe program. You can also print them, write it by hand and scan it back in, or write on a tablet. Do whatever you want, but the idea is that all the answers, the entirety of what you will turn in, is going to be within this document, this 8-page document. All right, so let's just do kind of some run-throughs about what to do with this lab. I'll probably say a bit more than I will from future labs that are based from the same website, because this is the first time we've done a simulation-based lab. Overall, I think these are wonderful. They're really well made, and they tell us a lot about astronomy. I mean, it's up to you how much you want to get into it in terms of the background information that's provided by the website. Although it's not overboard, it's just really kind of the right amount. They're short pages, which I'll show you. But I think it's just going to be a nice change for some of the at-home labs where we have to try to make things work just right. And so, it's really nice to have a combination of approaches here in astronomy. Kind of, really kind of getting your hands dirty, so to speak, maybe looking at the actual sky, and then doing something that is clean and elegant and works just like you want it to, like these simulations on this website. Well, let's take a look at the website itself, all right? So here it is. We can see that it is astro.uni.edu. All right, so this is the astronomy education at the University of Nebraska-Lincoln. This is their website. So they put this together. I'm going to take one step back, although this is the link that I provided in the same page that has this video embedded. But if you take a step back, you can see here are some other labs. The ones that are selected here are ones that I've taken a look at in the past and used in classes. Some of them, in fact, you'll notice are listed in the syllabus if you kind of look at these names. So these are ones we're going to be doing in future weeks. You can take a quick look and see what's upcoming. It's not like we're only going to be using these labs in future weeks, but we'll be using a subsection of them as we move forward. So let's go back to the basic coordinates and seasons. Take a look. All right. So there's always an overall description of the lab, a little screenshot that shows you what to expect from some of the simulations. All right, then we've got the document, some instructions, some places to go for instructors, and so on. This is the PDF that I actually uploaded to Canvas. But now let's get down into the main content. Right, nice label there. It tells us that that's where you want to look. All right. So once you have the student guide in front of you, then you can look at the main content. And this is going to have some background pages, for example, units of longitude and latitude. This is explaining the ideas of latitude and longitude, which are also explained in your textbook. But this can be a quick place to just take a look, kind of get an idea of how these different systems work, how they apply to the sphere of Earth, and thus also the celestial sphere, which of course we'll be talking about. All right. Then we have a little extra page which tells us about finding latitude and longitude, gives you some ideas about how to form triangles and think about it in a geographic or geometric sense. All right, and we got a bit of history. Definitely check that out, although it is optional. All right, so now let's move down. All right, so you can see here that there's a couple of these SWFs, right? Anything that has an SWF next to it in brackets, that's actually going to be a simulator. All right, and there's always going to be part of the lab. There's usually more than one simulator, sometimes just one. This one has quite a few, which is good and bad. It means you kind of got to move from one to another. You got to reload a lot of pages, but they'll work really well in most browsers. They're not Java based or anything, so they run very well. All right, so we can take a look at one here. We've got a map of the Earth, and we can actually move this dot around. All right. Before I get ahead of myself, I'm going to go back and kind of show you where these simulations come up in the lab document, the student guide, which I just called the lab handout. All right. So let's make this a bit bigger. All right. So you take a look here, we've got an introduction, and then we say, open the flat map explorer. So the lab is really clear about when to open what. So then obviously after you've opened the Flat Map Explorer, I'm just going to give you a kind of overview and then I'll circle back around. Once you open the Flat Map Explorer, there's going to be places to put information, right, that you complete within this table. And then you continue down, complete this table, answer the question in the place provided, answer some follow-up questions, and then finally get to the second part. The parts aren't numbered, but they are clearly labeled with a heading here. And then we notice we then are going to go ahead and open the Flat Sky Map Explorer, or the Sky Map Explorer. Okay, it's really up to you. And let me see, I think you might have actually had an option in the first one. Actually, no, it specifically wanted you to open the Flat Map Explorer, and then, although I missed it, the Globe Explorer at a separate stage. So just prior to question 4, it asks you to open the Globe Explorer. These are all simulations, and I'll show them to you briefly in just a moment. All right, and we'll go on, and it actually tells you kind of go back and forth at this one, the open different simulators. Here it just outright gives you a choice, because it's really up to you kind of which one is easier for you to read, so to speak, right? They both serve the same purpose. And then there's going to be questions in order to actually use those simulations. And as long as you're really using the simulations and really kind of following the directions, you'll have no trouble really answering the questions. I mean, obviously some of the interpretation questions really do ask you to think about astronomy, to sort of think about it in a more detailed way. Maybe, those can be a tripping point potentially, but I think you can certainly kind of gather the information that you should be looking for and focusing on when you answer those questions. But the ones that are just number questions really just rely on correct use of the simulation and, really clicking the right buttons. But, regardless of that, it's still fun, it's engaging, I hope, and it's going to teach you a bit about astronomy. And as far as, kind of that level of interpretation, say, this one is really kind of a yes or no, which direction. But over here, right out of the description, of the ecliptic, really this is in your own words, right? Well, how do you get that? How do you synthesize information to get your own words to write? Well, the best place is going to be this background information, right? All of these different sections, when I haven't showed you, celestial equator, declination, right ascension. I click on that and it's background information. It's a really, really nice, concise summary of the ideas that then you would need to kind of process and put your own words into to answer, like, say, something like question 10. All right. As we continue on, then we're going to open the another simulator, the Seasons and Ecliptic Simulator. And at that point, you can see that's the one at the bottom of the page. So it's really telling us we're on to our last simulator, right? And this lab has more simulators than usual, but they're also fairly basic simulators. So, there's a trade-off there. And we go in, and this actual last simulator is by far the most, has the most options and really the most information you'll be looking at. And as you can see, there's a much longer kind of detailed explanation of how to interpret what you're doing, tip boxes, and so on. So this is one to pay attention to. And if I recall, I think if you look here, on the background reading, it also, is not necessarily more in depth, but actually really has some ability to control things here within the background. So you can really kind of see what's happening. If I change the angle of the sunlight, what does that really mean, right? Well, it means that the sunlight's spread out. And, this is an idea in astronomy. This is the same amount of energy, all right, whether or not it's spread. And so when it's directly overhead, that same amount of energy is focused on a very small area. But when it's at a steep angle, well, now that same amount of energy is spread out. So then the energy per area is less. And if energy per area is less, that means that the overall surface of the Earth will heat up less because, you got to heat up the whole surface. And so, that's the idea about why we have seasons and it's colder in certain times of the year. Notwithstanding the fact that also the days are shorter. But in addition to the actual length of the days being shorter, this angle of light is of paramount importance. I think this does a good job of explaining it. All right, but let's just go ahead and run through all the simulators because we've covered where all of them are going to show up. So the very first simulator really doesn't have anything to do with the sky, right? It's just saying, okay, well, let's understand latitude and longitude as if maybe this was a geography class, right? A social studies class. And so you're going to go through, you're going to have, kind of certain locations, that you're going to find. You just got to fill in where there are blank spots. So here it has the center of the island of Madagascar and it asks for the latitude and the longitude, all right? So let me just show you that as an example, all right? And, I'll try not to give you all the information. So here we go, right? So you need to find Madagascar. A quick Google search can tell you where it is. And so Madagascar is going to be right here. It's this big island, okay? And again, I was trying there not to show it to you, so you can do it for yourself. But you're going to center the dot over the center of Madagascar. And there you go. It's going to give you your latitude and longitude, and you're going to figure out which one is which, right? And that's the information you're going to fill in. And then here you're going to look at a particular latitude and longitude, and you're going to say where that is. What country that is. What ocean is that. So it's kind of fun. You get to look on something like Google Maps and find out what that particular longitude and latitude apply to. And you're going to keep going. You got a famous city here, São Paulo, Brazil. Okay, so that's pretty straightforward. Then you continue to do similar things, and this is all going to be based in this same simulator. Okay. But then we get down to the globe simulator. So let's show you that. All right, here's the globe simulator. Same sort of idea. You can drag the point around. But you might say to yourself, well, unlike the flat Earth simulator, right? And of course, that's a flat Earth projection, not an actual flat Earth. this globe simulator is restricting me to just North America, kind of a little bit of Africa and Europe. Well, what you do is you click Shift, and the directions are here. Shift and click. So I hold down Shift and I click, and now look what I can do. I can turn the Earth with my trackpad, and now I can see the entire planet, okay? And if I click on a point, it will give me the latitude and longitude, right? I can drag it around. I can also click individually, like so. All right, so that's it. And you're going to answer some questions, and you can go back to the Flat Math Explorer, continue to answer questions. North Pole, what's its shape? Just really make sure you can read a map. All right, so now we're going to get down and do it for an astronomy map, okay? So the first one it wants you to do is the flat sky map or the sky map. But I mentioned this before, but let's see, right? I'm going to show you both of them, and it's going to be ultimately up to you which you prefer. All right, so this is the flat sky map. The idea is this is the same idea, really, as taking the Earth, a spherical map, and stretching it out imperfectly over a rectangle. Here we've taken the celestial sphere, which is already a bit of an abstract idea, and stretched it imperfectly over a rectangle. I say imperfectly because inevitably all the stars along the poles get stretched a lot more than the stars along the equator, all right? So everything actually is accurate, pretty close to the equator, but it becomes really distorted and over enlarged as we move away. Right. One thing we can see is we can see the Milky Way as the bright band of stars that is kind of across the sky. We could even add things like the ecliptic to make a little bit more sense of it. Although I always felt that the ecliptic is kind of confusing on one of these flat star maps. When we see it on an actual celestial sphere on the globe map, the globe style of looking at the sky, the ecliptic really does look so clearly like a belt that's a little jaunty, right? That's shifted to one side. And we can really think, oh, well, that's because the Earth is tilted relative to the sun. So of course, we have to have that tilt show up in terms of the way the sun shows up in our sky, right? Because that's all the ecliptic is just the manifestation of the Earth's axial tilt. But that's a big focus of this lab, is understanding like ideas like that. So if that's something that you're still kind of working on understanding, then absolutely, that's where you should be at in these type of labs. But obviously the other option that you can use for any part of this lab, of this section of the lab as we move forward, is the Globe Explorer. And not the Globe Explorer, the Sky Map Explorer. So it's flat and then without flat. And this one looks a lot like a globe. And it's the same thing. I can hold Shift and click, and I can move it around. I can clearly see all the different parts of the sky. And they're not distorted now. They're more accurate. And I can click on locations, and it will show me the values of that location. Now, latitude and longitude is pretty straightforward on Earth. It's really going to be, both of them are going to be in degrees. You can see that when we talk about the celestial sphere, we kind of have a little bit of a different approach. It is inherently a little bit more complex. The idea of longitude is going to be represented in terms of hours, and that's just because the 24 hours represents a full circle. So here it's 11. That's kind of the equivalent as like halfway around from the arbitrary starting point. So if I shift click over here, we can see the arbitrary starting point. This is like the meridian on Earth, but it's the celestial meridian. And as we measure it away from that point, then we get to a point that's almost on the other side of the Earth. And indeed we could see that because here is that same line that is going all the way around the circumference of the sphere. So we're almost at the 12-hour mark, or exactly on the opposite side of the sphere. And then the idea of latitude has a different term when we talk about the celestial sphere and locating stars. Instead of being called latitude, it's called declination. And it's negative if it's below the equator, and it's positive if it's above. So in fact, declination has a lot more in common with latitude. Really, we just changed the name. The actual form that it's represented as negative 24.8 degrees, is exactly as you would see latitude. The shift going from the Earth globe to the celestial sphere is more dramatic in terms of longitude, because we don't call it longitude anymore, which I guess is true of latitude. But in calling it right ascension, which is also a kind of weird term maybe, right? But we also actually changed the units. We're not representing in degrees. Now we could have just as easily called this something like almost 180 degrees, right? Because it's almost all the way around. But instead it's hours, which is actually not a bad idea, because the way the night sky moves, it actually makes a lot of sense for astronomers, and it's helpful for astronomers if they think about right ascension in hours, because then they know that as an hour passes in our time as an observer with your telescope looking at the sky, you know that the right ascension will have changed relative to you by exactly 1 hour. So there's so much reason to use the hour, but it does take you a second to make that transition from longitude measured in degrees to its celestial equivalent measured in hours. But again, 360 degrees was a full circle in terms of longitude. Now a full circle is 24 hours. You can also change it to sexagonal. This is just going to show you more detail. Basically split the degrees into minutes and the hours into minutes as well, instead of decimals. So it's completely up to you how you want to do it. In terms of splitting the degrees into minutes, that actually makes a lot of sense, because as we talk about the sky in other labs, we do tend to talk about arc minutes and arc seconds more than decimal fractions of degrees. So this is probably the better system to get used to, but also there's kind of questions within the lab that make you think about both. All right, well, let's just go back real fast and show you that indeed you're going to do some of the same sort of stuff. You're just going to locate some points. The points here, instead of being countries and famous locations on the map, the world map, are going to be actual sort of celestial events, equinoxes and solstices. And then we finally get into the last part of the lab, the season and ecliptic simulator. So let me show you that and we'll wrap up this video. This is a really neat one. So the idea here with the simulator, and again, there's a lot more directions about what it is and how to adjust it, but I'll just show you a few things that you can toggle around with. One thing, in this main window on the left, you can click and drag to change perspective. All right, so you don't have to shift click, you just have to click and drag. You can move the Earth wherever you want by just kind of moving it left to right, and you can change the perspective. Like if we're looking kind of head on into the Earth's orbital plane, it's like this. If we wanted to look, which would also be kind of the solar system's orbital plane as well. If we wanted to look directly above the solar system's orbital plane, it'd be like that. Right, and then we got the sun's declination and the sun's right ascension. That's its location in the sky. All right, but look, as we move Earth, right, as we're moving it in a path around the sun, we can see those values are changing. And the idea is they're changing because of the seasons, okay? They're just changing because of the location. But then, well, doesn't that depend where you are? Well, sure enough, it does. This whole simulator here on the left is actually tied in, locked to this little stick figure. So right now the default is for the stick figures to be on the equator, which is a really good starting point, because then we can say, okay, well, as I move around the equator, I can have these points at the equinox right here, where the sun is directly overhead, right there, and that's an equinox, okay? Sun coming directly overhead, kind of coming down. Actually, here, let's see. Oh, it's because my person's not quite on the equator, that's why. I don't know why I thought they're right on the equator. There we go. So if we put them right on the equator, actually, so the original starting point is a little bit north of the equator, not as far north as we are in Northern California, which is somewhere right around there. In fact, here, let's take a look. So click and drag the stick figure. Let's see. Yeah, so we actually can't put this over North America. This map is fixed in place. So if you need to think about kind of what your latitude is in California, you can just do a quick Google search, because it does show you the actual number. But anyway, we can put them up in kind of central Russia, right? Pretty far north. But anyway, I wanted to say the equator. And again, I misspoke when I said the stick figure is at the equator. If I looked more carefully, I could have told they're not. I think I saw them on a line. Anyway, so here they are. Now they're actually at the equator. There they are. Okay. And then if we get to the equinox, it should occur here in the orbit. So that's, let's see. So not quite. So basically, it's not like a lot of times when you look at figures of the solar system, it's going to be kind of like, fixed. But the thing is that this one is rotating. And so I can make that the equinox. So I could rotate it here and then even rotate it back to the overview. And now I've sort of set the figure so that this is the equinox. Okay, but since you can toggle it around, you can move the perspective however you want, the equinox can be located at any particular point. Like, it's not always going to be located here depending on how you move things. But the reason I know this is an equinox is for one simple reason, because the light is directly overhead for an observer at the equator on the day that half the Earth is illuminated exactly along a line perpendicular to the equator, right? So this perfect half and half along with straight overhead sun tells me I am a equatorial observer on the equinox, and I've defined the equinox at this location on the circle of the Earth's orbit. All right, ellipse, yeah, but nearly circle. Okay, but then on this particular day, what does the light look like for other observers? Well, as I move north, okay, it's still the equinox, so it's still a perfect day of of 12-hour days, right? Or, actually of 12-hour days. But even though the length of the day is 12 hours on every single part of the planet, you know what is not the same? The angle of sunlight. even if I go all the way up to the North Pole, right? At the North Pole on the equator, there is exactly at the North Pole, it's kind of weird to say that there's 12 hours of dark and 12 hours of light, because actually on the day, I said at the equator, what I meant to say was at the North Pole on the equinox. You might, does that rule apply? Is there 12 hours of sunlight and 12 hours of darkness? Well, not quite, actually, because that's the one point on Earth on that particular day, on the equinox, where what actually happens is the sun is just going to ride along the horizon in perpetual twilight or slash dusk or dawn, whatever you want to call it, for the full 24 hours. The sun will just go right along the horizon the entire 24 hours of that day. Okay, but if you're anywhere else, even if you're really far north, like above the Arctic Circle, way up above Siberia, you're then actually going to have 12 hours of darkness and 12 hours of light, because it's still the equinox. It's still a perfectly symmetric day experienced by the entire planet. But you know what's different about that particular day for someone way up here in northern Siberia as compared to someone over here right in the equatorial parts of the world, the tropical parts of the world, wherever you want to think, right? Maybe some island in the Indian Ocean, like Sri Lanka or something. Well, the sun is directly overhead, and look at that angle. The sun is beating right down on you, and we know, I mentioned it, if you read the background information, or you kind of saw the slides or the images early in this video, that means that the energy of the sun is concentrated in a smaller area. But up here, same length day, but the energy of the sun is stretched out. It's not concentrated on a small area. And so that angle of the sunlight is so important on the equinox, because it explains why, even though you get 12 hours of light way up here north, it's still not all that warm. Okay? It's still a long day, but it's a long, not very warm day, because that angle of the sunlight means that all that energy is spread out over a bigger area. It's smeared out over a bigger area. All right? But the thing is that this simulator, like I said, has so much flexibility, because it's not just about exploring the equinox. It's about exploring any darn day of the year, right? I can go to another day of the year, and look what happens, right? Now, unlike the equinox, where you got half the Earth illuminated right along that midline, look what happens, right? Now we have a point where clearly the North Pole is in perpetual daylight and the South Pole is in perpetual darkness, right? Just to kind of illustrate. But then we have all these ideas that now this is going to be summer in the northern hemisphere, and it's going to be winter in the southern hemisphere. All right, and let's go to the other one. Let's go around, hit another equinox, ta-da, and keep going. Look at that. Now we've got summer in the southern hemisphere, see, because we got a longer day, shorter night, and we've got winter in the northern hemisphere. But then winter isn't the same everywhere. Up here, winter's really, really severe. First of all, the day is even shorter, the night is even longer, and on top of that, the sunlight's more stretched out. As we go down south, we get to a point that even on the equator, on this particular day, which is, let's see, trying to remember if it actually shows you the day of the year. Wait, that's absolutely add labels to, and these are our celestial sphere coordinates. Not quite, because it doesn't, it's not really trying to propose a particular day of the year. But anyway, let me see, I just want to double check. Yeah, so these are just regions on Earth: equator, tropical Cancer, Arctic Circle, or Antarctic Circle and Arctic Circle, respectively. All right. But anyway, so, and you can actually see the sunbeam spread. This is the idea of the energy I was talking about. Look here. There's the energy spread out. And there it is concentrated. So I'll go back to this one. So I think it's pretty nice. Oh, you can change the view from the sun and then the view from the side. Okay. But my point was that on this particular day, on the equator, unlike on the equinox, right, we're still going to get, on the equator, every day of the year is 12 hours of light and 12 hours of darkness. And the lab might ask you that. So if I gave it away, I apologize for ruining the fun. So that's remarkable about the equator, right? Really special place, Every day, 12 hours of light, 12 hours of dark. Doesn't matter, because the axial tilt, you can see, right? What happens with axial tilt? It kind of pivots one way and then pivots back, but remains fixed at the equator. Right? That's the very nature of axial tilt. Okay, so, but we get back here. But what does change? The angle, right? So in different times of the year, it's not as hot, because as the sunlight becomes spread out over here, right, we'll say here, it's coming in at an angle, and then that means it's spread out. Those are actual cooler days, even though the length of the day is a full 12 hours. Right? So you go over here, now look, the energy is concentrated, and look, it spreads out. Not that much though, right? The change isn't that dramatic. So it's kind of subtle, right? There's just a subtle amount of sunlight intensity change throughout the year in the equator. Let's go up north, okay? So what's happening up here? Look at that change. Look, whoa, that's a big change. Now the sunlight is getting spread way out, which means you're not going to feel it very much. All right? Now going over here. And I chose a spot that's below the Arctic Circle, so there's no perpetual darkness. But what happens if I choose a spot above the Arctic Circle? Let's go back and add labels. All right, so let's go up above the Arctic Circle, which is pretty crazy north, right there. Okay? And let's go, right? Really, really spread out. Oh my gosh, that sunlight is super weak. Whoa. Oh, it's gone. Goodbye, sunlight. Wait for like 6 weeks to go by. Oh my God, more like 8 weeks. Oh, it finally comes back. Look at that. Look how spread out the sunlight is. It's barely there. All right, and it's coming around. Finally gets kind of intense. But look, it never even gets that intense, right? That's the intensest it gets. It was almost always intenser that year round at the equator. There we go. All right, so really cool. I think it does just a wonderful job of just thinking about what really makes the seasons. Okay. All right, so I hope this this directional video for the lab has really kind of shown you what to look forward to and answered any questions preemptively that may have come up. I still expect questions to come up, so please message me, and I look forward to seeing your lab reports. Thank you so much for watching this video.